Hi, welcome to Math 150, Section 1, Lecture 27. So today we're going to be talking about Taylor series and convergence. Does anybody have any questions from the material? So this is one of the most important parts of multivariable calculus. It's one of the greatest applications. The idea is to try to take a complicated function and replace it with a simpler function, which is easier to work with. And that captures a lot of the key features. We've seen an application of this when we did Newton's method. And we saw how incredibly powerful it is in terms of being able to quickly figure out the main behavior of a function. So for Taylor series, similar to many things in life, a lot of it is a function of how much computation do you want to do. The more terms you're willing to take, the better approximation typically you will get. But what's the trade-off? The trade-off is the more you have to compute with, the harder it's going to be to get nice closed form expressions. So when you're trying to figure out what's going on about a function, the big question is what information do you have at your disposal? And depending on what information you have, that's going to impact how you try to analyze it. So if you're trying to understand a function, what's the most important piece of information to know at a specific point? The outcome. So let's always make our point 0. So the first thing you might want to know is just what is f of 0? And then after that, what might we want to know? So I thought I just heard a beep. Nope. Oh, now the sound's working again. Excellent. Okay. All right, so things have been restored. So after knowing the value at a point, what's the next bit of information that you might want to know? And there's two acceptable answers. What might you want to know next? The derivative where? At that point. So the next thing is, if I can have two pieces of information, I would want to know the value of the function and the value of the first derivative at that point. You could say, I want to know the value of my function at the point, and I want to know the value of the function at another point. I want to know two values of the function. So there's several different ways you can go. If we're going to go the derivative route, which is not surprising given that this is a calculus class, then the next piece of information would be to know the second derivative, and then the third derivative. And then how many of you have ever taken a fourth derivative? Fortunately, for a lot of things in the world, going to second order is typically enough. For the fourth order, they often switch to Roman numerals, or more generally, people might put like a parentheses 4, and you know that it's 4 derivatives, and so on and so on and so on. And the idea is we want to approximate our function with a polynomial. So the nth order Taylor series at the point is just going to be f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared, all the way up to the nth derivative at 0 over n factorial x to the n, or just try to use our summation notation. The sum k goes from 0 to n of the kth derivative at 0 over k factorial x to the n. And so we're using the factorial function, which we talked about briefly last time, and we are using the fact that 0 factorial is 1. So 0 factorial should be read as how many ways are there to do nothing? How many ways are there to order just one object? Or is it to order no objects? There's one way to do nothing. There will never be another show like that. Why is this a good polynomial to use? Well, if you were to just start taking derivatives, you would see that the derivatives of this function at 0 match the derivatives of your original function at 0. And you would get that the nth derivative at 0 is going to be the nth derivative of our function for m less than equal to n. So if you just take the first couple of derivatives of the Taylor series, it's going to match with what's going on. And we go through this in great detail in the video. What happens if we take more than n derivatives? What would happen if we took n plus 1 derivatives of the Taylor series of degree n? What would you get? So what would we get if we took n plus 1 derivatives? Does everyone agree that this is a polynomial? What's the degree of this polynomial? N. What happens if you take n plus 1 derivatives of a polynomial of degree n? It's 0. What happens if you take 2 derivatives of a linear function? Ax plus b, it would be 0. If you take 3 derivatives of a quadratic, it would be 0. So if you take n plus 1, n plus 2, n plus 3 derivatives of this polynomial at 0, it's all going to be 0. So we don't expect the matching to hold forever. But if n is large, this is going to do a pretty good job. Okay, any questions about the general theory? So this is what's going on for one variable. And then we can calculate the Taylor series of standard functions. So in the video, we do cosine of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And an extremely important one is e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so on and so on. And it turns out e to the ix is cosine x plus I sine of x, where either I is or I am the square root of negative 1. And if you plug this in, if you replace x with I times x, all the odd terms, all the odd degree terms are going to have either I to the 1st power, the 3rd power, the 5th power, the 7th power. But what's I to the 5th? If I is the square root of negative 1, what does I squared equal? And so what does I to the 4th equal? 1. So every time you increase the power of I by 4, you return to 1. So when we look at what would happen if we put in ix, this would be ix, I cubed x, I cubed is going to be negative I, and then I to the 5th, that's just the same as I to the 7th, that's just the same as I cubed. And that's where this is going to come from. When you look at the even terms, when I replace x with ix, we would have an ix squared. I squared is negative 1. Ix to the 4th, I to the 4th is 1. So there's a beautiful relation between sines and cosines and the exponentials. This is where the angle addition formulas come from. The angle addition formulas are inherited from the exponential function. There's also in the notes, formulas for the log of 1 plus x and the log of 1 minus x. These are extremely valuable formulas to use. And so I'll just do the log of 1 minus x is negative x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4. How would you check and see if that's right? So I'm claiming that that's the Taylor series for log of 1 minus x. How can you check and see if that's correct? Yeah, it's like calculating derivatives. And so we have the function the log of 1 minus x. Now the first thing is, if x is a small positive number, the log of 1 minus x is going to be the log of a number that's less than 1. What can you tell me about the log of a number that's less than 1? What's the log of 1? 0. So if I give you the log of a number that's a little bit less than 1, should that be positive or negative? Negative. And you can see that it is going to be negative. So that's a good start. So if we take, not one of those things. All right. If we take f of x is the log of 1 minus x, f prime of x, the derivative of the log of 1 minus x, it's 1 minus x to negative 1. It's 1 over that. And then I have to take the derivative of 1 minus x. What's the derivative of 1 minus x? It's negative 1. And so we get f prime of 0 is negative 1. Okay? Now let's calculate f double prime. F double prime of x. So I take the derivative of 1 minus x to the negative 1 with a negative 1. So negative 1 comes down. That reinforces this negative 1 and it goes away. So I get 1 minus x to the negative 2, and I have a negative 1. And so f double prime of 0 is going to just be negative 1. What's f triple prime? It's just negative 1, right? Every derivative is going to be negative 1. Do we agree? Just because I have 2 data points, that's not enough for confidence. What if I did this and the first 17 all were negative 1? Then you start to get a little bit more confident. There's a beautiful, simple polynomial where it's first, if you evaluated the first 41 integers, it's always a prime. When you evaluate at 0, at 1, at 2, at 3, at 4, and it's a quadratic. It's a very small degree polynomial. And so when you look at it, it goes, wow, this polynomial is always prime. No. There's trivial reasons why it can't always be prime, but the pattern persists for a while. You've got to be very careful when you look at stuff like this. Just because it's looking negative 1, it's looking promising, but I want more data. Let's do another one. Let's do f triple prime. F triple prime of x. I bring down the negative 2. The negative signs are going to cancel. I'll have a 2 outside. 1 minus x to the negative 3, negative 1. What's f triple prime of 0? Negative 2. Let's do the next one. The fourth derivative. Now I have negative 3 comes down. It's going to hit the 2. The negative sign is reinforced. So it's going to be 3 times 2, 1 minus x to the negative 4, negative 1. What's the fourth derivative? That's 0. Negative 6. How should I view 3 times 2? 3 factorial. I should really view this as, I brought down I should really view that as a 1 over there. And if I view that as a 1, then this would be 2 times 1, 3 times 2 times 1. Oh, so this is basically just negative 4 minus 1 factorial, negative 3 minus 1 factorial, negative 2 minus 1 factorial. So with a little bit of work, you would show the nth derivative at 0 is just negative n minus 1 factorial. And now we can put in this into the expansion. So the nth order Taylor series is the sum, k goes from 0 to n, of the kth derivative at 0 over k factorial x to the k. So it's the sum k goes from 0 to n. The kth derivative is just going to be negative k minus 1 factorial divided by k factorial Well, k minus 1 factorial divided by k factorial is just k. So this is just going to be the sum. K goes from 0 to n of negative x to the k over k. So I just pulled out the negative sign, and it's just 1. I'm sorry. Better be a little careful. What is f of 0? Zero. So when I start to do this, be a little careful. When I substitute for the kth derivative of 0, I can write k minus 1 factorial for every choice of k but k equals 0. It's equal to n minus 1 factorial except over here. And so really the sum should not start at 0, it should start at 1. And so I'll just get x plus x over 2 all the way up to x to the n over n. And that's a really nice application of the theory of Taylor series. Okay. So what I'll do now is I'll just first ask you, are there any questions? And then if not, I'm going to just do a little video or a little mathematical exploration to show you how good of a job this does. Yes? Yes, so we will get to two-dimensional. So I want to do one-dimensional first. I'm forgetting that I can actually hit pause. Okay, so I believe people in TV land can see this. And so what I've done is I've defined some functions. So I'm going to look at the Taylor series of the function for, I think, cosine. So we're doing cosine of x. And here I have x naught, n, and c. So x naught is the point that I'm looking at. So as you look over here, you should hopefully see a giant dot moving. That's the point I'm going to look around. C allows me to zoom in and out. So when I look at cosine, how big of a window do I need to look at to understand cosine? I'm sorry? 0 to pi, or technically minus pi to pi, but it's symmetric. So we can easily get 0 to pi, giving us all the information we need to get us from negative pi to 0. Now the n factorial, we just saw in the last lecture, this is not a coincidence, that n factorial grows really, really fast. It's like n to the n e to the minus n. It's growing much faster than x to the n. So as long as we're just evaluating between negative pi and pi, the x to the n is going to grow much slower than the n factorial, and we hope that only a few terms will be needed. So what I'm going to do is I'm going to zoom in right now. And so this is now looking at a little bit more than 0 to pi, than negative pi to pi. And over here, n is going to be the degree of the Taylor series approximation. And if you look, it's basically a 0-order Taylor series approximation. And as I keep it's not showing the lines. Interesting. Oh wait, maybe. Oh, I didn't recompile this line. Okay, there we go. Let me just pause this for a second. All right, so I'm not sure why it wasn't working, but as a general rule, when things don't work, just reboot them. So I will zoom in again. And now you should be able to see a giant solid line at the top. That is the zeroth order Taylor series approximation, just using the value of the function. Well, it's also the first order Taylor series approximation, because if you remember, cosine is 1 minus x squared over 2 factorial. There's no linear term when we approximate cosine. Yeah, the derivative of cosine at 0 is 0. So the first order and the zeroth order are actually the same function. They're just both the function 1. And now what I can do is I can increase this to 2. And this is the best parabola approximation. And as I zoom in, is the parabola doing a pretty good job? So pi is about 3.14. What's pi half? Approximately a little bit more than 1.6. A little bit more than 1.5, less than 1.6. So you can see over here, we're not missing by a terrible amount. Going all the way up to 1, it's actually doing a fairly good job. The cosine is pretty well given by 1 minus x squared over 2 for a pretty decent region. Now, we know that this can't be good forever because the parabola is going to be going off to minus infinity in both directions. And cosine runs between -1 and 1. What do you think would happen if I looked at the third order Taylor series? Do you think it would be better? So why would the third order be better? Because, well, if you're adding more terms, it should do better. Will you add a third term if you do the third term of cosine? It's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. So the third order is actually the same as the second order. So if I increase this to the third order, there's no gain. But if I go all the way up to the 4th order, it's looking pretty good. And so now I'm going to zoom out a little bit. And now it's getting very close to 2 before I have any issues. So if I go up to the 6th order, and I've got things programmed right now so that if I just click on the plus button, it knows to go up by 2. I gave the computer a little bit of a hint not to bother with the odds. Let's see how well it's doing now. So with the 6th order, it's capturing it pretty well, almost between minus pi and pi. If I go to the 8th order, it's really hard to see the difference between the function and the estimation. What you would really want to do in something like this is you would want to plot not just the two functions, but what you want to plot instead. Not the derivative. The difference. Because they're so close right now, things are being dwarfed. Maybe it's much, much closer through here and it's less over here, but I can't really tell because they're all so good. They're drowned by the main term. And so you would want to just look at the difference of the two. And so, if I go up, here is, 12, the best polynomial of degree 12. I mean, that's almost a perfect fit. And if I zoom out, of course, it's eventually going to be bad. But for an entire period, it's almost perfect with the 12th fit. Okay, you could, of course, do something ridiculous. I could go to your polynomial of degree 38. And then I'll leave it to you to just estimate just how many cycles do you think you should be able to get as a function of the degree. But here, I'm still seeing incredible fits. Okay. The next thing I wanted to do is, this is one of my either favorite or least favorite functions in all of mathematics. E to the negative 1 over x squared. Have we talked about this function in this class? I think I may mention it as an extra credit problem. It's defined to be 0 when x is 0, and for every other value, we use e to the negative 1 over x squared. So here is the plot of the function. Okay? It's falling extremely rapidly. Well, if you think about what happens, if you take x to be 1/10, you get e to the negative 100. If you take x to be 1 over 100, you get e to the negative 10,000. Boy, this is crashing down. As x gets larger and larger and larger, it's looking like e to the 0. What is e to the 0? 1. And that's why you can see, as x starts getting away from the origin, the function is fairly rapidly approaching 1 on both sides. But as you crash towards 0, the function gets small really fast. Well, I'm going to zoom in. And this is one of the great features in Mathematica, this manipulate, is I'm telling it to plot the function of e to the negative 1 over x squared. X goes from minus c to c, but I can choose c between 10 and 0.25. So as I change the value of c, I can zoom in. And so here, I'm plotting it for basically negative 1/2 to 1/2. And you can see the function is essentially 0 on this range. If I zoom in a little bit more, we're now getting things of size 10 to the negative 11, and then dropping down to almost 0. It's really, really hard to see what's going on. This is a function where you should really plot not the value of the function, but the logarithm of the function. And that would be something that you could visually see. And I will talk about logarithms on Monday. This function is not allowed in complex analysis as a differentiable function. So when you get to complex analysis, it's very, very different because the derivative has to exist along any path that you come. In one-dimensional calculus, even in multivariable calculus, when we're talking about paths, well, for a function of one variable, there's really only two ways to approach a point, left and right. It's not that restrictive to say your function is differentiable. In complex analysis, it's more restrictive. This is somewhat similar to what we saw in multivariable calculus when we said it's not enough for the partial derivatives to exist for the function to be differentiable. If you try to replace x with z, where z is a complex number, z equals x plus iy, and see what goes on. Well, if I take z to be I times y, you would get e to the negative 1 over iy squared. That'd be e to the 1 over y squared. So as you approach along the imaginary axis, the function is actually going to plus infinity. If you approach along the x-axis, it's going to 0. The function isn't even continuous. So if you try to extend this to a complex valued function, you don't even have to talk about differentiability because it's not even continuous. This is similar to what we were doing with sequences and series, where if the terms aren't going to 0, it's not even worth trying to say, should I do the ratio test? Should I do the root test? Should I do the integral test? There's no need. The sum can't converge. Every derivative of this function is 0 at 0. So what would it mean if every derivative of the function is 0 at 0? It would mean that when you try to do the Taylor series, every term in the Taylor series is 0, so your Taylor series approximation would be identically 0. This is problematic. And so if every term in your approximation is 0, then your Taylor series is identically 0, but we know the function is not identically 0. So some of the big questions you have in Taylor series is, if I give you a Taylor series, does it converge? And then if it converges, does it converge to the original function? The Taylor series for the function I just showed you does converge. It converges to the 0 function. The only point where it converges to the original function is 0. This is not really worth celebrating because we write things as f of 0 plus something times x plus something times x squared plus something times x cubed. Well, if you take x equals 0, it has to agree because it's just f of 0. You're forced to agree at 0. It's not really that big of an accomplishment. But for any other point, it is tremendous. Yes? So for the function I gave you, so if you use L'Hopital's rule, all of the partial derivatives are 0, all of the derivatives are 0 at 0. And so when you then construct the Taylor series, it's just going to be identically 0. And so what this tells you is that the theory of Taylor series is a little bit more involved than you might think, that there are real issues about convergence. We are not going to cover those in this class. This is an introduction to the subject, but it's worth being aware of the difficulties and the challenges. All right. The next thing is to look at multivariable Taylor series. And so I'm going to keep this on the board. And so the question is, how do you extend what we're doing to functions of several variables? There is a big painful theory, and I'll give you a little bit of a sketch of the painful theory, and then I will show you a trick which doesn't seem to be taught, but it allows you to do almost every multivariable Taylor series if your function is nice. And since this covers most of the cases you will need to look at, I think this is really worth hitting. So what I could do is, let's say I have a function of two variables x and y, and I want to associate some Taylor series of degree n to f in two variables. Well, the way to do that is maybe to just match up derivatives. So I should start off with f of 0, 0. That'll be the 0 order term. Then I need terms of degree 1 in x and y. So we have something times x and something times y. What do you think the term times x should be? Because I want to match derivatives. So the partial derivative of f at x times x plus the partial derivative with respect to y times y. And if I look at what's going on now, if I now take the partial derivatives with respect to x and set x and y equal to 0, only this term survives. Now I can look at the degree 2 terms. So how can I get a degree 2 term involving x and y? What are the ways I can have x and y combined and have something of degree 2? I could have what? So the degree is going to be the sum of the exponents of x and y. So how can I combine x's and y's and have something of degree 2? I could have x squared. What else could I have? xy, and what else could I have? Y squared. So I want an x squared term. That's going to involve two derivatives with respect to x. So I'll have maybe d squared f dx squared at 0, 0. And then I'll have d squared f dy squared 0, 0. Now when I think about this, when I take two derivatives with respect to x, all of these will vanish when I take two derivatives with respect to x. This will vanish when I take two derivatives with respect to x. But I'm going to get a 2 factorial coming down. So what do I need to divide this by? I have to divide this by 2 factorial to make the derivatives match up. And then I have my xy term, and it will be fxy at 0, 0. And I don't need a 2 factorial down there. And you can just continue to higher and higher degrees. You can interpret the terms in different ways. The first order term, I can view this as the gradient of f times the vector xy. If I view it like that, that's really what's going on. This is the generalization of f prime of 0 times x. The next one is a bit harder, is you have to view this as a matrix. fxx, fxy, fxy, fx, the fyy. And if I view it like this as a matrix, if I multiply things out, I'll get fxx times x, fxy times y, fxy times x, fyy times y. Then I have that vector over there. And when I do all the algebra, it's going to come out like this. The 1 over 2 is going to give me the 2 factorials here and here. And the fact that I have fxy twice is going to have things reinforced so I don't have a 2 down there. It gets worse when you start looking at the terms beyond degree 3. But what we're trying to do is we're trying to interpret how can I generalize f prime of 0 times x. Well, I can view this as the gradient of f dotted with xy. I have to be careful because now the derivative of f is a vector. How do I view f double prime of 0 times x squared over 2? It turns out the way you view that is it's 1/2 x f double prime of 0 times x. And you convert this to vectors and matrices. And just when we replace x with xy, how can I actually combine these things? And that's where this is coming from. So rather than going into the full general theory, I just wanted to just give you a quick rough sense of where it's coming from. Okay, so this is in principle how you would start to calculate all these derivatives. And this is how you would in principle calculate second order, third order, fourth order Taylor series expansions in several variables. You can see that if I just add more and more variables, I just have more and more terms. And it's going to become a nightmare. So what I'm going to do now is I'm going to show you a quick trick that allows you to do a lot of these problems very easily. So it is essential if you want to use this that you know how to do one-dimensional Taylor series. And this is why I am trying to keep these functions on the board. So let's say I give you f of xy is cosine xy. We can now start calculating the partial with respect to x, with respect to y, with respect to x twice, xy, and so on and so on and so on. Or let's say u be xy. So let's say, what is the degree for Taylor series? Well, we know the cosine of u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial, and so on and so on and so on. So the cosine of xy is just 1 minus x squared y squared over 2 factorial plus x to the 4th y to the 4th over 4 factorial. If I want the degree 4 Taylor series, what's the degree of this term here, x squared y squared? 4. What's the degree of this term? 8. So it would just be 1 minus x squared y squared over 2 factorial. This is much better than calculating all the partials and putting it together. So if I can write my function as something whose Taylor series I already know, I can just substitute it in. What if I gave you f of xy is cosine x squared plus y? What should we take for u? X squared plus y. And then we would get cosine of u is 1 minus u squared over 2 factorial plus u to the 4th over 4 factorial minus 1 to God. So the cosine of x squared plus y is 1 minus x squared plus y squared over 2 factorial plus x squared plus y to the 4th over 4 factorial, and so on and so on and so on. Now, if I want the Taylor series of degree 4, is every term here when I expand going to be of degree 4 or less? Yeah, when I expand this, I'm going to get an x to the 4th, I'll get an x squared y, and I'll get a y squared. What about x squared plus y to the 4th? Will I have any degree 4 terms from that? What terms from x squared plus y to the 4th will be degree 4? only the y. I have to take y every single time. This is really 4 factors. X squared plus y, x squared plus y, x squared plus y, x squared plus y. When I multiply it out and use the distributive law, if I ever choose an x squared, that'll give me something of degree 2. And even if I choose y every other time, it's still only going to give me something of degree 5 as the lowest. The only way I can get something of degree 4 is to take the y every single time. And so if I only care about the degree 4 Taylor series, I would say that this is y to the 4th plus higher order terms. So HOT stands for higher order terms. And so the 4th order would just be 1 minus x squared plus y squared over 2 factorial, and I could expand it out if I wanted, plus y to the 4th over 4 factorial. And that would be the 4th order extension. Yes?
It's really nice that we can substitute in different approaches.
Yes.
At the same time, not exactly sure because for the function that we said into the one of x squared, if we just substitute negative 1 over x squared into the third, we don't substitute.
Correct. But of course, you can't substitute 1 over x squared because when x equals 0, that blows up. You can't plug, you can't take e to the x and plug, or call it e to the u, and you can't let u equal 1 over x squared because when x equals 0, it blows up. The problem is the Taylor series doesn't converge for that function. You are correct that there are some issues. And the issue there is that that function u is a terrible function. For that problem, u is equal to 1 over x squared. Here, u is xy, u is x squared plus y. These are very, very nice. I could do the cosine of the square root of x and y. And things like that would work out nicely as well. This method crucially involves special functions that we know well. And if we ever have a function that we don't know well, we're stuck. But when you are doing mathematics, you don't go back to square one and rederive everything from the beginning. You use results that you already know. So if we know results from one-dimensional Taylor series, if we know tangent and cosine and sine and e to the x, why not use them? And then rather than doing all the calculations from scratch, let's just jump ahead. The other way to look at this is it's a two-stage process. We first construct a related function of one variable. And that variable u is a nice function of x and y. And now that we have that nice function of u, we Taylor expand that. Then we replace u with the x's and y's and expand everything out. So this is only going to work if you have nice inputs. If not, you then have to go back to the more advanced, more painful method. All right, any questions about this? So at some point, I will talk about the birthday problem or the birthday paradox. How many people do you need in a room before you have at least a 50% chance that two people share a birthday? The answer is surprisingly low. Does anybody know roughly what the answer is? It's around that. And I remember one year I was participating in Windows on Williams. And as a math professor, I always like to bring some kind of fun math to the event. And so I got permission from admissions that if there were not two students at the event with the same birthday, everybody at my table would have free admission to rooms. And he was a little concerned at first. And I said, I will commit to paying 10% of the tuition. There were over 100 people at the event. So the odds with over 100 people in the room that you don't have two students sharing the same birthday is so small, I was willing to do this. But it made for some very eager students at my table going around the room and asking people, what's your birthday, what's your birthday, what's your birthday? And I think they only had to go one or two tables over with their own. The probability is extremely high once you get up to 30 or 40 people. There is a way to solve this exactly using very painful products, And there's a way to approximate the answer by using Taylor series. And so with 5 minutes left, it's not really enough time to go into this with Taylor series. So what I'll just do is, I just want to make sure people know the binomial theorem. If I give you x plus y to the n, this is the sum, k goes from 0 to n, of n choose k, x to the k, y to the n minus k. You might know this from Pascal's triangle. And this is what you get when you expand out x plus y to the fifth. These are the coefficients. It's going to be 1x to the fifth plus 5x to the fourth y plus 10x cubed y squared plus 10x squared y cubed, and so on and so on. So n choose k, algebraically, it's n factorial over k factorial n minus k factorial. It's the number of ways of choosing k objects from n when order does not matter. Think of it as representatives rather than offices. I claim that this is the same as n choose n minus k. You could prove this algebraically, but you can also prove it by a story. Anybody know who the Sneetches are? Sneetches on the beaches? It's from Dr. Seuss. There are two types of Sneetches on beaches. There are those with stars on their belly, and there are those that do not have stars on the belly. And initially, the people who don't have stars on the belly are made to feel bad. In the end of the story, we realize that it doesn't matter if you have a star on your belly or not. If I choose exactly k from n to have a star, that's the same as choosing n minus k not to have a star. And so a lot of times when you're trying to prove things in combinatorics, we do proofs by story. That if you can come up with a nice story for what's going on, you can explain and avoid doing a lot of algebra. At a higher level, there's a lot going on. So this is an extremely important formula. One way to see why this is true is, let's have x plus y to the fifth. So we have x plus y, x plus y, x plus y, x plus y, x plus y. When I expand it out, I'm going to get terms that will involve x to some power and y to a power. But I know from each factor I choose either an x or a y. So if I choose 3 x's, I have to choose 2 y's. If I choose 4 x's, I have to choose 1 y. If I choose k x's, I have to choose 5 minus k y's. How can I choose k x's? Well, I have to choose k of these factors to be an x. So that would be, say, if I choose k. Once I choose k factors to be an x, how many factors are left? I started with 5, I chose k, how many are left? So you have 5 factors, I choose, so let's say I choose 2 of them to be x's. How many factors are left if I have 5 initially and I choose 2? 3. So in general, if I have 5 and I choose k, there's 5 minus k that are left. I have to choose all the ones that are left to be y's. So it's 5 minus k, choose 5 minus k, choose all of them. What's 5 minus k, choose 5 minus k? 1. If you have 6 objects, how many ways are there to choose 6 objects from 6? Take them all. If you have 4 objects, how many ways are there to choose 4 objects from 4? Take them all. Because this is 1, people don't bother writing it. And so really, this should be here. We should really have in here an n minus k choose n minus k. Well, since n minus k choose n minus k is 1, we don't bother writing it. But at a fundamental level, that's really what's going on here. All right, so this is Taylor series. Monday is going to be our first review class. So anything you want to see and review, happy to do. I will do a little bit of a lecture on logarithms and exponents. I think that's worth doing. But other things you want to see, just let me know. Friday is the third mental health day, I believe. So there's no class on Friday. All right.